for the invitation. I do appreciate the opportunity to come and speak with you all. It always feels a little bit awkward, like speaking to medical profession folks. And I say this coming from a perspective. I do actually have a practicing doctor brother, so like it's not completely lost on me. But I also always do feel like the dumbest person in the room when I get to speak with you folks. So again, I appreciate the opportunity to share a little bit of weather knowledge with you all. And Dr. Drummond hit on something that I think is really important, that a lot of our work, like regardless if you're in medicine or in my place, it's weather and climate. A lot of this, the impacts of weather, climate, all of these things, it's interdisciplinary, right? It's not just getting in your own little silo talking about what, in your case, medicine, in our case, weather. It touches a lot of disciplines out there. And to be able to understand that, to be able to reach across the aisle and work with people and to speak the same language, I think is incredibly important. So I think it's really good that you all are in this course. I believe it is an elective, right? So you don't have to be here. But getting a little bit of appreciation that stepping outside of your normal confines and experiencing things that you may not be fully aware of, I think is really cool. So I'm just going to be sharing a little bit about extreme weather, and in particular, like how the weather and climate space is kind of evolving with time. And putting this together, I have actually shared this presentation with Dr. Drummond before, so you may not get any new nuggets this time around. It just happens to be one of those things that I didn't have a whole lot of time to put this together, but I'll just lead off with a really quick summary of climate change. Are things going to get better or worse for us as a community? And I could probably just make this a 20-second presentation, to be honest, because as we probably already understand, climate change will make things worse pretty much across the spectrum for all of us, whether it's extreme cold or severe weather or heat, monsoon, thunderstorms, drought, like the whole gamut. Like there are signs that things are going to get worse, and unfortunately, it's just something that we're going to have to become more resilient to. I will touch briefly on a lot of these, so we'll just kind of go through it one at a time. Um, Starting with extreme cold, which is one which is it's a little bit strange. We don't normally associate extreme cold as getting worse with climate change, which in most cases means a warming of the earth. But we do actually find that there are cases where extreme cold will get worse. And part of the science behind that is you all have maybe heard in the news, there's a lot of buzz terms when you listen to the weather. One of them, when it comes to winter and extreme cold, is the polar vortex. And it's probably taken out of context, if we're being honest. It's just one of those hype machine type things. Bomb cyclone is another one that's kind of become big in the hype machine world. But there is some truth to that. So the reality of what happens is, climate change, it does mean fewer cold events. The world is warming, and there's nothing really to dispute that. But if you look at some of the details, what this climate change actually does is it destabilizes the atmosphere in a way that it basically creates more kinks in the jet stream. And the jet stream is basically what steers weather systems through, especially during the winter in our neck of the woods. So when you have more kinks in the jet stream, that means you have potentially more warm events during the winter, but it also means the potential for more cold events. So with the help of machine learning and a lot of statistical analysis, what we find is that, yes, there are going to be fewer cold events, but there might actually be more extreme cold events, meaning the really, really cold events that we all kind of come to hate. Um, One recent example that I think of, at least, it's relatively recent memory for me and my brother, who was actually impacted by this event. He's actually staying with me right now, so he can speak to this. So a few years ago, there was a cold event that hit the eastern US in December of 2022. And in particular, it hit Denver very, very hard. And the net result from that was Southwest Airlines, in particular, had such a hard time dealing with the aftermath with the airlines trying to catch up. And in that case, it was a computer system that just was not able to hold up to it. It completely broke down the airline system. And for about a week, maybe a little bit longer, what we found were that more than 18,000 flights were canceled over the course of, again, like a week. So it really snarled travel, again, during kind of a peak holiday timeframe. I mentioned my brother, he was staying with me over the Christmas holiday that year and was not able to fly back to Washington, D.C., which is where he lives. So instead of catching a flight back, he ended up having to rent a car for extreme prices because everybody was renting cars trying to get back to their destinations. So this was just one quick example of something where, again, we see more of these potential extreme cold events that cause significant issues to economy, to medicine, et cetera, et cetera. One quick summary, then this is just a quick recap of what happened this past winter. So this is a temperature ranking of what we just experienced from December through February across the continental US. And obviously what jumps out is across the Western US, including most of Arizona, this was the warmest winter on record. And by all accounts, it wasn't even that close. Number two is a distant second at this stage. But what we find, actually, if you look closer, is that the northeastern US actually had a pretty cold winter here. And again, my brother, who's staying with me right now, mentioned that this is one of his, well, it was a memorably cold winter in DC. So climate change is kind of impacting us disproportionately. And even with extreme cold, I mean, you'll find that that has an impact on the medical system and the number of people that are coming into hospitals checking in because of frostbite or whatever type issues that they might experience. Moving on, and feel free to jump in if you do have questions, by the way, open a discussion. Severe weather, I mean, this is one that probably is not a surprise. Things would get worse with time. And so just the very basic background on the three ingredients to generate a thunderstorm. It's moisture, lift, and instability. So when you think about climate change, and in particular, heat, since we are moving toward a warmer world, what we find is that at least the moisture and instability elements are driven by temperature. So these are the areas that potentially generate, that are influenced in a climate change world. One thing that, and again, we're in a weird scenario where we're kind of in the middle of it and the change is happening, and sometimes it's hard to statistically categorize what exactly is happening. Part of the challenge is we have a lot more people that are able to report and are impacted by thunderstorms nowadays. So it's hard to categorize the difference between what's actually happening because of climate change versus what's happening just because we're more vulnerable or there's more people or that sort of thing. So that's something to keep in mind. But one of the things that we have proven is that there is actually a shift, at least in the climatological locations for tornadoes. When I grew up and when Dr. Drummond grew up, like our generation of folks associated Tornado Alley with the Great Plains. I grew up in Kansas, so like it was just a thing that we knew to shelter in place. We knew exactly what to do when a tornado hits. As it turns out, like Tornado Alley of 2026 might be a little bit different than what was the case about a generation ago. The trend is actually for tornadoes to be more commonplace in the southeast. So we're talking Arkansas, Mississippi, Alabama, Tennessee, Kentucky, that general area. And we're actually seeing fewer tornadoes, especially in the deep south, so Oklahoma and Texas. It's an interesting trend that I'm not sure we know why exactly, but it's definitely happening over the course of the last decade or two. And when you think about it, when you overlay that map, again, more tornadoes in the southeast, and you consider the element of where are our most vulnerable populations. On the map on the right is a social vulnerability map. So the deeper colors, more socially vulnerable. Well, now we're hitting locations that are much more at risk for tornadoes to begin with. There's certainly a lot of mobile homes in that general neck of the woods. There's a lot more trees. One of the things that we learn in the weather world is that people oftentimes don't act upon like a severe thunderstorm warning or a tornado warning unless they're given more evidence that this thing might actually impact them. So whether it's a TV meteorologist telling you got to get to shelter, or looking out the window and actually seeing something. In that location, in that general neck of the woods, I mean, it's really, really hard to spot tornadoes. I mean, there's a lot more trees. Driving around, it's just a lot more difficult to get around. So these are all factors. Oh, I mean, consider also a lot of the homes out there, they don't have basements. Growing up in Kansas, you just kind of know that shelter in place in your basement. Well, a lot of that just isn't there in the Southeast. That infrastructure isn't in place. So for a lot of these considerations, you're seeing a lot more impact because of this gradual shift. Again, that's a downstream impact for you folks who might see, again, an increased response because of things that people may not be prepared for. Okay, we'll move on to the monsoon. So localizing it here in the Southwest a little bit and talking about severe weather. Um, there's been some research on this front. I won't consider myself an expert in this area. I've only lived here for 5 years, so that's an element too. But there is research that suggests that rainfall has actually increased here in the Southwest since the 1970s. It's probably also kind of one of those makeshift things where you'll have periods of extreme precipitation followed by more extreme drought than what we had experienced in the past as well. So again, climate change makes things worse on both ends. Extreme drought, when we go into drought, it's a worse phase. And when we go into flooding situations, it's probably worse floods as well. It's hard to predict exactly where we're going from here. We do expect, again, because of climate change, the higher temperatures and potential for more moisture, that is fuel for thunderstorms. So the potential is there, and the expectation is that thunderstorms become more intense. But it's also entirely possible that they become less frequent in the future as well. So that is maybe our new normal, is that we get similar precipitation and it comes in much shorter duration and much more intensity. So these are things that, again, just from a resilience standpoint, that point we're still trying to kind of come to grasp with and trying to plan for in the future. All right, we'll move on to ocean circulations. And this is something that probably most of us don't really think about when it comes to climate change. I know that I don't either, especially living here in Arizona, but it might actually have a pretty large scale impact in the time frame of, let's say, generations. It's not necessarily something that's going to happen today or tomorrow or next year even. So I remember growing up in grade school or middle school or high school or whatever it was, we talked about the North Atlantic Drift or the Gulf Stream and what that is. And this was before I became a meteorologist. So I do remember, talking about those young years, how the Gulf Stream, it's basically like just this warm conveyor belt of moisture and temperature that brings some of the heat in the Gulf of Mexico and the southern Atlantic Ocean up toward northern Europe. And I've learned again, and since my science and my background in meteorology, that it's because the Earth is the way it's set up. Basically, it's always going to try to find it like an equilibrium state. So the equator locations of the Earth, they're always going to warm disproportionately compared to the Arctic. And part of the reason of these ocean circulations is to bring everything back in balance. And to do that, you basically just bring some of those warm temperatures from the equator up to the polar regions. And the Gulf Stream, for what it's worth, is actually one of the most efficient ways to do that. So that's the reason why it exists. It's absolutely integral to bring the Earth back into equilibrium in a way that you're cooling off the equator a little bit and you're warming up the polar regions with this Gulf Stream. Hopefully all of that makes sense. That probably wasn't the best description of it. But that's basically more or less what it does. What we've learned with climate change is that, and in particular, Greenland's ice sheets, we probably understand that they are melting, and that's pumping fresh water into the North Atlantic Ocean. And you folks with your background, you probably understand it actually better than I do with your background in chemistry and that sort of thing. That because you have now this relatively warm moisture that is low in salinity being pumped into the ocean, well, I should step back a little bit and mention that part of the pump of this entire ocean circulation is actually in the North Atlantic Ocean. And that's because when you have that cold, high salinity water, so really, really salty, cold water that's very dense, that actually, because of those density differences, that's what actually causes sinking oceanic water in the North Atlantic Ocean, which drives the entire ocean circulation across the Earth. It's because of those density things that are occurring in the North Atlantic Ocean. Well, as it turns out, because of this Greenland warming ice sheet and the pumping of the fresh water into this location where the pump of this ocean circulation actually starts, there's actually a weakening of this ocean circulation that's taken place. And research has shown that this ocean circulation, so the Gulf Stream, has actually weakened by about 15% since the 1950s. Again, that's mostly because of the warming of the earth, climate change, that sort of thing. And stepping back, just using our conceptual model now, that if we have a weakening circulation, that means we're not as efficiently pumping that warm air from the equator up to the poles. And apparently, according to research, this has actually happened many, many times in the past, the shutdown of this ocean circulation. It's not to say that it's going to happen in the future, but we're pretty confident that it's going to continue to weaken here in the next years and decades. And that potentially has a net effect of, again, if your circulation is weakening, then the equators are probably going to get even hotter than they are right now. And the poles might actually be moderated a little bit. Yes, the globe is still warming, but it might be actually counterbalanced by not as much warm air being pumped by this ocean circulation. So it remains to be seen how this will play out exactly, but it is something that we'll need to monitor very closely because these ocean circulations have a huge impact on potential climate in the future. Hopefully all that makes sense. Cool. I'll wrap things up with heat because obviously that's something that's very near and dear to us here in Arizona. And I'll just share like a few graphics that we've kind of put together over the years. And I'll do it through the lens of heat risk. So this is a product that the National Weather Service has put together that's actually built around the impacts that we've seen related to extreme heat. We're all familiar with temperatures, and obviously the hotter it gets, the more impacts you'll see heat-related illnesses and heat stroke, that sort of thing related to heat. Well, doing a lot of research, we were able to actually define thresholds based on when we start to see some of those impacts and the general population versus the more vulnerable populations, and when we start to see some of those impacts. And so there's a lot of data that actually goes into this, including the climatological normals of a specific location, the highs and lows, the time of year that you're talking about. A heat wave this time of year, like 100 degrees, let's say here in March, is going to hit you very different than 100 degrees in the middle of July. There's an acclimation process, obviously, that the human bodies go through. So a lot of those considerations, overnight relief, that sort of thing, are thrown into this product, NWS Heat Risk. And we drilled that all down into a 5-tier color product that, again, it's the forecast is basically just one of 5 colors, but it factors all of those into place. So it can run from anywhere from green, meaning there's no risk for heat for this particular day, to yellow. It's going to be warm and potentially impactful to our most sensitive populations, talking about the elderly, the very young, those folks. And the higher up you go, the more impactful a heat wave might be. At the magenta level, we're talking about something, if you have, much of any exposure to the heat, it's going to impact you, without protections. We're talking water or shade or whatever it might be. And these magenta heat waves, they are long duration as well. So that's the highest tier that we have on this NWS Heat Risk product. So starting to look at, again, some of our data as it relates to Arizona, and again, through the lens of this NWS Heat Risk product. What we're finding, this chart for what it's worth, is actually just counting the number of days in between, I believe, April and October of every year, and just counting the number of days that fell on green versus yellow versus orange or red or magenta. So it basically gives you a quick summary of how hot a year was, as measured by heat risk. And what you'll see by the trend is that there are more and more orange and red and magenta days as you move from left to right in this chart. And it starts in 2005 for what it's worth. And this is for Tucson. So it is locally calibrated here. So we are seeing more orange and red days with time. And one thing that kind of jumps out to me is that you don't even see any magenta until roughly 2017. So basically, another way of characterizing that is how we define long duration extreme heat waves now in 2026. They did not even exist here in Tucson prior to 2017. It gives kind of a stark example of just how hot we've gotten here in Arizona and kind of where we're going as a state, unfortunately, when it comes to heat. All right, next bar chart, again, related by heat risk. Here, we're actually pairing the data with emergency department visits. So we have a great relationship here with the Pima County Department of Health Services and the state level as well. And they're able to share some of their heat-related illness data, basically the number of people that are checking into hospitals reporting heat-related illnesses. And we can pair that up with how hot it was by an NWS heat risk perspective. So this data goes back to 2018, and it's basically a cumulative number of people that are checking into hospitals. And we can run it for inpatient data as well. But this is just people that are reporting heat-related illnesses by sheer number. And what you do see by this chart, again, this is like a cumulative number by year. Our hottest years were 2023 and 2024. It's not really a huge surprise if you've lived here the last few years. It's been really hot, and those were actually our hottest years. One trend that I see in this chart that I think is actually meaningful in a positive way is that if you look at just the yellow color, it actually is in a downtrend over the last 6 or 7 years. And again, our definition of yellow is warm days that, for folks like you and me, we might be a little bit uncomfortable if we're outside, but it's not going to give us those heat-related issues. For folks that are disproportionately impacted, so the elderly, heavily medicated, infants, etc., those folks are the ones that are impacted by yellow level heat. And to see that that number is basically on a gradual decline, that's actually a positive thing, I feel like. As a community, it feels like we're actually making a difference on that front. We've focused a lot of energy on trying to support those folks. And I think that we're actually seeing trends that we're making a difference. Okay, next graph. Again, we're looking at the emergency department visit. And this is a histogram. So we're basically just plotting it out by frequency. The data that was presented to us by the Arizona Department of Health Services, it's a day-by-day tracking of heat-related illnesses across the state. So we're able to look at that day by day, and we're not, again, necessarily comparing it against the heat risk color here, so I don't have those heat risk colors. But we're just plotting the sheer number of heat-related illnesses by day. And not surprisingly, most of our days are going to be kind of on this low HRI front, meaning warm days and not a huge number of people checking into the hospitals. And you see kind of a logarithmic decrease in that number with time. But we are kind of curious about those days that you have a ton of hospital heat-related illness folks checking into hospitals. Like, what is the character? What does the weather and climate look like for those specific days? So we took a quick look into that here, and in particular, those days that were reporting over 1,000 heat-related illnesses per 100,000 visits. So a huge portion of the population that's checking in with HRIs. They had all of these things in common. And for what it's worth, it was 19 days since 2018. Actually, it was 15 days. Sorry, I had my math on. Every one of them, actually 93% of them, fell on major or red level or extreme level magenta heat. They were almost all long duration heat, so 3 days or longer. And they almost all occurred between mid-June and mid-August. So those are the extreme days that we're really focused on. And if we wanted to narrow it further, 67% of them were in July. So that's really kind of narrowing the scope of what we're paying attention. When are these days that folks are most at risk to heat? The one exception for its worth actually occurred in early June. And our belief it was because we actually had a relatively cool spring that year, and then we jumped right into a heat wave. So an early season heat wave that people were just not prepared for the heat. So that's what happened with that one exception, the 7% from this. Just one quick bar chart. Again, we're looking at the same data here and we can plot it in a different way. So again, we have HRIs on a day-by-day basis, and we're able to plot that as a bar chart. So any single given day versus, again, the number of people that were checking in for that specific day. So this is, you can read it as just like a bar chart. And we also color each individual bar by how hot it was by NWS heat risk. So that's what this bar chart is. And it's exactly the data that I was kind of describing. This was 2023 for what it's worth. And if you were here in 2023, you may recall that that was the most brutal summer that I think that I've experienced here at least. We went through a roughly 2 to 3 week period where temperatures were 105 to 112, I believe, every single day. And there's just very little overnight relief. So you do see that here as well. Again, those were all red heat risk days. And if you can see my mouse, I don't know if you can see my mouse, but in the middle of July, that's what this is. And they have, again, very high bars, meaning a lot of HRIs were being reported on those days. And it's all red, meaning, very, very hot days. So we're seeing the correlation day by day here. All red, meaning they were very hot days, and a lot of heat-related illnesses being reported. There's a lot of things that we can kind of glean from this sort of chart. You can actually see by a single day, by tracking it just by a single day, the most heat-related illnesses that were reported in a single day was actually this one here. It fell on an orange day. But like I was describing before, we had a very cool spring leading up to it. So I think people were just kind of caught off guard by relatively cool spring days. And then we jumped right into a heat wave. There are other factors that we can kind of learn here too. Like there's this yellow day here that has a significant number of heat-related illnesses. I think that what we were finding there is what actually happened was right at the end of this heat wave, we had a really strong thunderstorm that moved through town, ended up causing something on the order of 50,000 power outages across town. And as you can imagine, with that number of power outages, it just took a long time for TEP to get in there and just really start to fix things up and get people power back where they needed it. So the way I almost kind of imagine it with these really strong thunderstorms during the monsoon here, they help to cool things down, and that's a really great relief. But they also bring the power outages, and if we're not able to get power back for these folks up in time, inevitably, the heat comes back here in Tucson. So if people are still without power and the heat comes back, we start seeing issues again. And this is a very clear sign of that here. So I believe that is my last slide. Again, I thank you for your time, and I'm here. I don't really have anything going on today, so I'm happy to, if you have any questions for a meteorologist, I'm sure, you don't get the opportunity to interact with our kind too often. It doesn't necessarily have to be heat related, but I'm here to have discussions and just chat. Thanks again, Dr. Drummond, for the invitation.